Good day, everyone. Welcome to the 11th World Congress on Information and Communication Technologies 2021. Title of our presentation is Automatic Modulation Recognition Models Based on Transfer Learning and Simulated Radio Signals in Additive Wide-Diffusion Noise Channels. My name is Jami Orotmi Olashino. These are the outlines of the presentation: introduction, methodology, result, and discussion, conclusion, then acknowledgement and references. Then the introduction. Communication is an integral part of every society, and without this communication, the whole world will be in a serious dilemma. Therefore, the need for telecommunication. And this telecommunication is due to the modulation and demodulation. And either of these can be achieved using analog or digital techniques. Due to the advantages of digital techniques over analog, then digital techniques is used in the study. Because the disadvantages of noise level in the case of analog is so disastrous in this regard. Apart from this, there are more digital communication techniques than in analog, and also the like of anti-interference that make digital to be more reliable and resilient is a key. There are also a lot of variations that are possible with the use of digital modulation and demodulation, and this has broadened the scope of radio communication in the domain of software-defined radio. In non-cooperative condition, as a category of data communication, automatic modulation recognition can be applied between signal detection and demodulation phases. And as such, NCC has applications like signal confirmation, identification of interference, confirmation of interference, countermeasuring radio signals, and spectral management. As one of the applications of software-defined radio, which is the automatic modulation recognition, has prompted the need to generate 15 different digital modulation for both line of sight and non-line of sight under additive wide-Gaussian noise. And we also consider the signal ratio values ranging from -20 decibel to +20 decibel with steps of 5 decibel. And what is this AMR? It is a blind detection of modulation types, and this is done at the receiving end. And these techniques will help the cognitive radio to opportunistically use the free frequency band without any disruption to the original primary users. And this AMR can be achieved by any of this method: likelihood-based method, feature-based method, machine learning-based method, or deep learning-based method. And out of all this, deep learning is the state-of-the-art algorithm, and this has disengaged the need for feature extraction, like in the case of the handcrafted algorithms, machine learning, and the likes. Convolutional neural network as a deep learning algorithm is a handy tool, and it is widely used for automatic radio modulation. The modular classification system for AMR by authors in some of the papers reviewed had been limited to low values of signal-to-noise ratio, and it was only able to identify 3 number of modulation schemes. Besides, we encounter 11 digital modulation that achieve good results of training and validation of 87.4% and 99.8% respectively. And this work had a limitation of not being able to cater for various signal-to-noise ratio with large data set. We also encounter a paper with training accuracy of 82.8% when the data were considered for both line of sight and non-line of sight, with varied signal-to-noise ratio, although very small data sets were considered. And of course, 97%, 94% accuracy attained by one of the author, one indicator for signal to noise ratio between -10 decibel to +10 decibel. And this has enabled us to identify gap. In our work, we make signal to noise ratio between -20 decibel to +20 decibel for both line of sight and non-line of sight under the additive white Gaussian noise. And we did this for 15 different ether modulation that are frequently used in majority of our communication standard. And another intention is to have a closely related data set to a real-life data set, and this for real-life application. The methodology. We acquire our data in the environment of the GNU Radio Companion. We preprocess the data. The data were trained and validated, and thereafter, the model built was tested with out-of-sample data set. And this particular explains how we have labeled our data set for the training. This figure explains how we have been able to demonstrate the generation of our data set for each modulation schemes. 2202.27 by 227 by 3 pieces of AlexNet data input was considered using the transfer learning approach. And above all, 21,600 data samples were trained. An evaluation of the model was performed using 5,400 samples. The two balls in the MATLAB 2020A was also considered for this work, and there we consider the stochastic gradient descent moment and categorical cross entropy was equally used. The ReLU was the activation used, except that at the last densely connected layer where ASPMIR was used. The learning rate was considered to be 0.0001 and batch size of 10 and validation frequency of 30 were equally considered. Figure 3 and Figure 4 showed data before and after processing. And Figure 5 shows the entire data that were used for this training. According to Table 1, the validation and testing are presented. And from this table, for our model that was built with line-of-sight additive white Gaussian noise, the latest validation and testing accuracy of 93.33% and 80.00% were obtained at -20 dB, and it is an expected result since there exists a distortion at very low signal-to-noise ratio values. However, there are major improvements at higher value of SNR. And of course, 100% validation and testing accuracies were achieved. And evidence of this are shown in Figure 6, 7, 8, 9, and 10. And the results of our model are better off compared to some of our literatures, despite their lower number of modulation classes. As it has rightly been said, Figure 6, 7, 8, and 9 proved the result, and this is Figure 10, showing the variation according to the Table 1. In conclusion, the preliminary results obtained in this study have no doubt proved the efficacy of our AMR model developed using the transfer learning approach with AlexNet pre-trained architecture and constellation data set for both LOS additive white Gaussian noise and non-line-of-sight additive white Gaussian noise. Notably, all the validation accuracies are from 91.67% to 100%. This model shows potentials for incorporation in a modern-day wireless receiver to aid software-defined radio and cognitive radio functionalities. And being the preliminary result of our ongoing research work on multitask wireless signal recognition, WSR, our future work will involve exploration of more simulated data sets, as well as over-the-air data set in real-time wireless environment with harsh characteristics. We hope to come up with a more robust multitask WSR models from our endeavor that can be leveraged for software-defined radio and cognitive radios functions such as spectrum sensing, automatic demodulation, and spectrum management in 2G, 3G, 4G, 5G, beyond 5G, and also Internet of Things and Cloud Federation use. This our work was performed in the ASPMIR laboratory, a laboratory at the Covenant University, and also the High Performance Computing Node of the Covenant Applied Informatics and Communication Africa Center for Excellence, Capicase, Frederick Textbed, and that place we use for our experimentation. We also acknowledge the Office of the Davis Research Innovation Engagement as well as the Institute for System Science and KZNE Skills Collab, Durban University of Technology, Durban, South Africa for collaboration on this work. These are our references. Thank you, and God bless you all for listening.